Swayam Prabha. Digital India. Educated India.
Welcome to the subject Advanced Digital Image Processing and Computer Vision. Today we will have its first lecture and we will discuss about the topics on image representation, then principles of imaging, and also some of the objectives and problems in computer vision, and a few operations on image processing. So let us first consider that how images are represented in computer. Let's look at this particular image which has been displayed from its computer representation itself in the digital form, and when we display in the display screen, you can see that it looks like a photograph, a two-dimensional photograph, and there is a brightness variation across the points in this particular display screen. So the way this information is stored in the computer is that it can be stored in the form of a two-dimensional array. So let me explain a little bit more. So suppose let us take a very small, a kind of a small portion, rectangular portion of the image, and expand it further. So zoom it there. So if you just concentrate on that part, you can see that enlarged portion of that image, and here you may find that edges are getting blurred or jittery, and even the textures, they are also becoming coarser. But overall the structure what is there within this portion, those are also reflected here. Now you take a very small portion once again from this image. So what you will find here, you will find all these information, the points which you are observing, actually they are kind of smooth rectangular or square blocks of having certain brightness level, some brightness level. So those levels, for the sake of convenience, I have shown with certain numbers. So larger the number, brighter the respective box. Now these are the values which are stored in a two-dimensional matrix form, a two-dimensional array form in the computer, and each value, so one element of the array denotes some points. So for example, this one may be a point in this portion, in this image, and or if I go to the original image, this may be somewhere here, this may be somewhere here. So the point is that every element of that array is mapped to a point in the space, and which is displayed, which is used for displaying this distribution of the brightness level over the screen. And the value, it is showing the level of brightness with which that point should be displayed. So an image, essentially we can say that it is a 2D array of integers. It could be real values also. So in this case, the representation is in the form of integers and positive integers in the discretized form. So one of the thing what you would like to know, it is just because it's a representation of an array, then you should know what is the size of the array for which this image is displayed. Say for example, if I consider this full image, so its height is across this dimension. So this height is 384, which means the number of rows of the array is 384, and width, which is across this horizontal direction, this is the number of columns, and the value here is that 256, height is 384. But if I consider this portion, naturally is number of columns and number of rows will vary, will be different from this one, in fact smaller, and but it is a mapping. But even though it is smaller, but when we are displaying it, we are displaying in a larger zone, and that's how the various the coarse structures, those are getting more and more visible because it is taking more and more areas to display. So that was about the representation of an image in the form of a two-dimensional array. That is how computer programs deal with images in the form of a data structure. Now, when we represent a colored image, as many of you might know that actually it is the color mixing law that is applied for producing the color or for rendering the color points. So, which means that every color can be created by mixing three at most three primary colors. And so one example of primary colors is red, green, and blue. So the definition of primary is such that if I use any two of these color, I cannot produce a third color by superpositions or by mixing. So let us use that term mixing. We will understand it better when we discuss about the color processing. So when we capture an image from the environment, the color of that particular visible point or surface point, they are stored into the form of these three primary, whose mixing would produce the same color. So that is the principle by which color images are captured, and that's why color images are captured into three components. One for the red, here it's shown, usually it is red, green, blue. These are the three primary components which are used. So each of them can be is represented by a two-dimensional array, which means for a color image you require three two-dimensional arrays. Say the previous one where I have shown the black and white image, but actually the black and white image is converted from a color image, is transformed. It was generated from a color image. So it had a red component, green component, and blue component. And if I superimpose them in the display device in the same positions, respective components with the same color is displayed. So the effect would be effect of a display of a color image. So for color image, you require three two-dimensional arrays. Now, when we store an image in a computer, we have to, as you know, that any entity in a computer is stored in the form of a file. So image is also stored in a file. Though image is of a say two-dimensional array, let us consider only this form of image like optical image. So it's a two-dimensional array, either three two-dimensional arrays or one two-dimensional array. So but there is a structure. But when it is from a file, you have to actually store it like stream of bytes. That is what computer that is the technology for computer for storing information. It should be a stream of byte, and that is how it accesses the information from the secondary storage or from the file itself. So in this case, that's why when we store the image, it is not sufficient just to store those values of brightness levels, or we call it pixels. Those as just in some scan, linear order, you just store it, because you have to interpret that image. When you read this file, you should know that how this image should be again reformatted into its proper structure, like in the two-dimensional array form. So those information which is necessary to represent the image in this array form, those are also stored in the image file in the beginning, and we call this information as a header. So many of such information would be there in header. I just I have given examples, some of the very essential elements like width, height, the dimensions of the array that you require. Similarly, number of components. Say for color image it is 3, for black and white image it is 1, or even there are satellite images like multispectral images. We call the number of components could be very large. For hyperspectral images, it could be as large as few hundreds itself. So that's why you require this number of components, and then you also require to store the conventions by which this stream of bytes should be converted into the value for a pixel. So number of bytes which is required for representing an integer or real number or different formats. So all those information, they are stored in the header. So when the program reads the file, it's first reads the header, and there are known formats by which this header is read and this information is extracted. We call it parsing of header information. So from there you take individual information, and then finally you read those stream of bytes as stream of pixel values and get the image in its proper format. There are various standard file formats which are available, which are proposed by different international bodies and used in different applications. Say TIFF, BMP, GIF, PGM, PPM, JPEG. It is a format for compression standard. DICOM, it is a standard for representing medical images. So different such formats are available. But once you know that format, because they are all standards and their documents are available, so you can, given a file into that format, you should be able to extract the image. Let us come to the basic principles of image formation, and particularly in optical camera. And with this example, we would also try to understand some of other cases. So when we consider an optical camera, we say this scenario, say this is an object, and we can see this is basically a tree. It's a schematic diagram, and you have the camera, and the camera has a plane within itself where this image is formed. So this plane could be the film of that camera. So when you place the film, so that film defines that plane where the object points are projected, so they are focused on that plane, and we call it focal plane then. But you put a film, so you will record the points in the form of a film through the optochemical reactions. Or it could be a sensor, optical sensor, say some CCD element or CMOS element, which will transduce the optical energy received at that point into an electrical energy. Then you sense the level of energy that is received. So they are arranged in the form of plane, and every point in that plane is basically mapped, indexed through the placement of a sensor and addressed by the corresponding technology. So you have a coordinate system in this image plane, and you have also a three-dimensional world. That means an object in the 3D coordinate system. So if I consider any object point in this surface, so basically the light is incident. The light is, so for the incident light at that point is getting reflected, and then it is passing through the lens of the camera. So as you know that from our physics, school physics, that the center of lens is the point where every rays passes through, remains undeviated. So that is what I am showing here. So as if so you draw a point, a ray passing through its center of lens, and then that one where it intersects, even if you extend it, and where it intersects the image plane, at that point you get the image of the object point. So we call this point, say this is small p. So small p is the image of the object point p. So this is the image formation rule. If I consider any other object point, say you consider another object point. So if I construct a straight line passing through this center O, so you can, and then you extend this one. So where it intersects, now that points become the image of this. Suppose this point is Q, so image is formed as a Q. Okay. So this is a principle by which we can find out that how images are formed. So this rule is called projection rule. That how do you project 3D points on the 2D plane. So for this rule, what are the two things necessary? One thing is that in this case you should know where is your image plane, and you should know what is your where is your center of lens. So we call it center of projections. So your lens of the camera defines that, and image plane defines that. So given these two parameter, center of lens and definition of the image plane, your projection of any point of three-dimensional point will be defined. Just to explain once again, suppose I take this point. Once again, you see that this is my center of lens or center of projection. So what I will do, I will first form a straight line passing through this, and then the line where it intersects, say where it intersects the image plane, there. So once again, if I consider, say this point is R, so this is a projected point, say smaller, right. So this is exactly what is happening. But what is the function of lens in this case? So that also let us try to understand. So function of lens, for understanding function of lens, what we know that as per this lens is a convex lens. So what it does, it whatever energy it receives from the point P, it converges. It basically tries to put it on the point where it is forming the image. So it is converging them. All those rays are becoming convergent, or it is focused to the image point. That is the purpose of also doing focus, which means the energy received at this point. So energy received at this point P is proportional to the energy reflected from this point. So this is the idea. Suppose you have a point Q. Okay, so let us consider a point Q. So in the same way, I can say that fine, I will form the image, say at this Q, and the energy reflected from Q, so they would be convergent to this point because of the lens action. So the brightness variation, it is so if you don't have the lens, the received energy is very feeble, and the variations among them will not be perceptible or will not be properly captured. But with lens you are magnifying that operation. So you are getting you are drawing most of the energies reflected at that part onto this one. So that is the purpose of using a lens, and lens gives a brighter image. Otherwise it would look very faded and brightness variation would not have been understood. So this is a function what it takes place for optical image, and as I mentioned, rules of projections, just once again to summarize, that you have a center of projection that defines one of the parameter of this or configuration of this projection. Then you have this image plane, and given any object point P, if I draw a ray passing through the center of projections, where it intersects the image plane, there it forms the image. That is the rules of projection, and this type of projection is called perspective projection. But there could be various other principles. There are other images. So this is not the only imaging principles. There could be many other imaging principles. So one other simple example could be, I have considered the projection rays, formation of the projections rays in the case of perspective projections, that all rays should pass through the center of projection, and then where it hits the image plane, intersects the image plane, that is the image points. But instead we may consider all projection rays are parallel to a given direction. So for any point you consider, and then you just consider some parallel directions, and all the rays are parallel to this. So here we have given an example where the four corners of cube are projected even parallelly on the image plane, and wherever it intersects the image plane, those are the points of projections. So this is called parallel projection, and one of the examples of parallel projection is the X-ray imaging of the X-ray system. So X-ray plates, where X-rays are parallel beams which passes through our body, and wherever it gets occluded, and wherever it falls, it basically with certain degree of absorptions it intersects, and we get those kind of impressions. So this is parallel projections. There could be various other modalities of imaging, imaging principle, other modalities of imaging could be there. Say you consider a surface profile and let there be a transmitter which transmits the ultrasound wave. So, it transmits the wave and then it also reflects the wave, and the reflector and there is a receiver which receives it. So, what you can do with this mechanism, you can measure the distance from that point to the surface point, because if you can observe the time difference of transmitting start of transmission and point of reception, that is called time of flight. And then the velocity, if you know the velocity of the wave, for example in this case sound wave, and then in that medium, and then you multiply with the time, it would give you twice of the path it travels. So, that would give you the distance. Not only that, the amount of energy that it reflects, and that is what you have received, that also provides you some kind of material properties. So, it gives not only the distance but also these properties, and this mechanism, sensing mechanism, could be coupled with scanning of the beams, and you can get multiple, you can get observations for various points on the surface profile. Now, ultrasound images is one example. Here I have shown one of the echocardiogram frames, where it is the heart's chamber which are being displayed, where your sensor, your ultrasound is transmitted and it is traveling through the heart tissues, and at various stages it is reflecting. So, each reflection is giving the kind of distance where that point is there, and the amount of reflection is also giving certain kind of tissue properties. So, finally, if I say in a very abstract sense that what is an image? What do you mean by an image? One very simple way to say that it's an impression of physical world. So, that is one of the I should say motivation to get images, to understand the physical world better, or sometimes where you do not have any access, then by taking images from different mechanism, you try to get a glimpse of what is going on there, and then interpret it to understand this world better. Also, for the purpose of recording, as you understand, that is also needed. When you get an image, you can record the phenomena. So, impression. So, it's an impression of the physical world. In a more objective manner, you can say that it's a spatial distribution of a measurable quantity encoding the geometry and material properties of objects. You consider this optical image in the two-dimensional form. As I said, it's a two-dimensional distribution of brightness values. The brightness you have measured, and in that arrangement, in that distributions, as we can understand the geometry and material properties of objects, those are encoded into that, because those that distribution depends upon the geometry and material properties of objects. Also, the lighting source and other things are also involved. So, this is about images, and then we process these images, etc. So, what about computer vision? As you know, the computer vision also very much related with image processing, because it uses images. So, but now what is meant by this kind of vision? The term vision comes as if it's a visual system for a computer. The way human vision, we understand the human visions, like a human being, it understands the scene, understands the world by looking at it, by visual sensation, and then interpret it. So, the objective of computer vision is also something like that. So, it is but that is the facility to be provided to the machine. So, this is the science of facilitating human-like capability of seeing and understanding the environment to a machine or computer. So, this definition is taken from the British Machine Vision Association. So, this is a website, and you can also go get this definition. To elaborate it further, like we have eye, similarly camera is taking the role of an eye, and it is sensing the environment, and through that optical sensing itself, and then it is capturing the image of the environment, that's impression of the physical world, and those are basically taken to the computer. Those data are taken to the computer, and then computer through computation processes that information and tries to understand it. So, in a more precise way, what we can say that computer vision, it concerns with the automatic extraction, analysis and understanding of useful information from a single image, or not only from a single image, from a set of images or a sequence of images. And also it involves, that means as a subject, it involves the development of a theoretical and algorithmic basis to achieve automatic visual understanding. So, these are few objectives of the computer vision. Some of the examples I can cite here, very typical problems of computer vision. Say to determine structure and geometry of objects. That is one kind of problem. It could be to determine material properties of objects, or to determine objects' position, category and its role interaction with other objects, and to enhance our perception of the physical world. So, these are few problems, but there could be various other problems. So, with this background, some kind of representation of images and its storage, its imaging principle, and also its relations with the computer vision, the term computer vision, the subject matter of computer vision. Let me quickly go through some of the concepts and operations on digital images in my subsequent part of these lectures and also in the subsequent lecture. So, first thing what we will here understand that the histogram of an image. So, as we understand histogram of any variable, it is basically it is a frequency distribution, and in an image this measurable quantity is that variable, and for example, for an optical image it is the brightness level. So, brightness level representation in a typical optical image where you require 8-bit representation of a pixel, it varies from 0 to 255. Say you consider the scanned document which has been shown at the left side. So, there you can see there is a text and over black text over the white background. So, there in this image we have brightness levels of various degree of brightness. So, the background is brighter, whereas the text which is the foreground which is darker. So, this is a distribution. By looking at this image, at this distribution itself, so histogram what you see, so this is a histogram here at the right side, that frequency variation. You can see there are more white pixels than dark pixels because the range is showing it. So, histogram gives you first level statistics or first order statistics of the image. And if I normalize a histogram, then which means that if I divide the frequencies by the total number of pixels, then actually it is giving some kind of estimate of the probability value of those pixel values. It is reflecting certain kind of properties or characteristics of an image. Now, one of the operations of an image, the previous example I have just shown, is called binarization operation, or I have also mentioned thresholding, because the threshold effectively you are determining at each point whether the value would be foreground value or background value. So, there is a simple way of doing it, is that you determine some threshold value, the threshold range. So, now if your value is less than that threshold, then you consider it belongs to one of these class, either foreground or background, and vice versa. So, the task, as I mentioned, separation of foreground from background, and the simple operations could be that in the previous example I already told, foregrounds are dark pixels which are text, backgrounds are bright pixels which are white region. So, there if I get the pixels in a binarized image, then we will be basically setting into two of these values. two value, set to one of these two values, either 0 or 1 or 255 or 0, whichever we think that would be convenient either for the purpose of display or processing. So anyway, so in our case now we have assumed say 255 is one level which is denoting background pixel, and 0 is one level which is denoting foreground pixels. Now conversion of an image into this form is called binarizations. That means you are separating background from foreground. So a very simple algorithm, that's the term thresholding will be clear by this algorithm, that if I choose a value and we call it threshold value t, it's a numeric value, and if a pixel is greater than that value, then we set it to 255. That is the background white part, and otherwise we set it to 0. So one good example could be that now how do you determine it? So one of the guiding principle could be just look at the histogram and try to see that where actually, because you know that darker part is foreground and brighter part is background. So when you see that the frequencies start rising at the higher range, so at that point you may consider that that should be a threshold point, because those ranges are showing the foreground part, and the other part should be background. The higher part is background, the lower part is foreground. But the problem here is that visually, if you try to determine, it is not really giving any kind of objectivity. I mean, you have some guess, some idea, but there are a lot of variations. So, for example, you could consider a value at threshold is say 156. Say you may consider this is the value 156, or you may consider another value say 192 by looking at this just rising trend of the histogram. You are choosing these two values, and now if I apply this thresholding operation on one of these two cases. So first we are considering with the 156 value. So this is the result what you see, and for 192 threshold, this is the result. So naturally you can see that in the previous case where threshold is 156, there the text looks little faded. That means some of the text, some of the pixels which belong to text, they are classified as foreground. So they are made white by turning them to 55. So you are missing those points. So that's why it looks faded. Whereas if I use the threshold 192, so those pixels which were earlier not detected as text, now those are detected because you have increased the threshold range. But by doing that, what happens that some of the noisy part also, which were certain in that range, those are also becoming text. So you are introducing, you are making some of the background pixels as the foreground pixels. So it looks more, though the contrast has increased, it looks more noisy. So the point is that can we think about some algorithm, some reasonable computations, logical computations by which we can determine an appropriate threshold and by which we can automate this operation. So one such method that I will be discussing here to give you an idea that how these computations could be done. As you understand, it's a classification problem, that classification between foreground pixels and background pixels. We will be considering one of the classification technique. If you have gone through the machine learning course, you know there is a Bayesian classification technique, and we will be using that for detecting the foreground and background pixels, or classifying a pixel either into foreground or background. Now the statistics what you have about the variable brightness value, as we have already discussed, that the probability distribution is you are getting the probability distribution from this histogram itself. You can compute it. So finally you get the probability distributions. So this probability distribution gives you the probability of occurrence of value of x. Now we consider that there are two classes. One is foreground and is background. These two classes will determine that so the belongingness of the pixel's value is largely dependent on the contributions from either from the foreground phenomena or from the background phenomena. So that's why when you have two classes, we can say that what is the probability of x which belongs to the foreground. So given a foreground pixels, that means you consider text pixels, there is certain probability distribution, certain possibilities of having brightness values of a pixel, certain probabilities. Similarly for background, certain probabilities. So we can consider the probability of x as a as it can be factorized into this form that, so probability of x is that either it is coming from the class W1 or omega 1 into probability of x given W1. So let us take W1 here as the class 1 and plus probability of W2 and probability of x given W2. So that actually accounts for the probability of that pixel x. For Bayesian classification rule, what we will do, we will compute rather the probability of a class given that observation. So that is called posterior probability. So we will compute probability of W1 given x and probability of W2 given x, and we will assign the class to x, that class to x whose probability is larger. So this is the rule. So how to compute this posterior probability? So for that we can use the Bayes rule, Bayes theorem, that a posterior probability, that probability of, here I have shown with respect to class nomenclature omega in general. So for the class omega given x is given by this expression. That means you have in the numerator probability of omega into probability of x given omega divided by probability of x. Now this is coming from the joint probability of x and omega, that rule itself. So this is called class prior, and this is called likelihood probability of x given that class, and this is called marginal probability of x. Now in these computations, as you observe, that we want probably to compute this one, and since x is same, so it is sufficient if we compute the two quantities. So effective computation of x is not required. Just two quantities if you compute, and then you can use it for comparisons. So how do you compute the class prior? There we assume that this histogram has as I said, from the histogram we will assume that the dominating part of W1 is primarily dominated, the part of the class 1 primarily dominated by these probabilities, and similarly it will also give you some this part is primarily dominated by the other likelihood probabilities, and then their contributions are also, so this is a kind of zone which is overlapping zone, and where you have the prior probabilities are also acting in particular in doing these computations. So once what we do, we estimate these probabilities using certain thresholds. So we can consider, we use an expectation maximization algorithm. So we assume that, let us consider some value, threshold value, beyond which is one of the class, and say mostly it is dominant class is W2, and the other side is W1. So with this division, you can compute these proportional areas, area of the part for W1 and for the W2, and you can estimate the class priors, like probability of W1 and probability of W2 from the proportional areas of each region. And then again, for each region, through parametric estimation, you can also compute the likelihood probabilities. So by assuming this Gaussian, you can compute its mean and standard deviation. Similarly, for the other one also, you can compute its mean and standard deviation. And then it is, I'm just showing that what is the that normal distribution or the Gaussian distribution, how the Gaussian distribution looks like. So if you know the parameters, if you know these parameters mu and sigma, you can compute what is the probability in exact terms itself. And then what we do that, and this is the way these parameters are computed. And finally, we can compute the new threshold value, so that for x less than threshold, this is that means with these parameters, now you find out the point of transitions where the one probability, that is the posterior probability, is becoming higher than the other one, right? So then you know that this is a transition point, and with this new threshold value, you just iterate till the value of threshold converges. So this is the algorithm. We call it expectation maximization algorithm, because we start with an expectation that this is the threshold value, then we maximize these probabilities, posterior probabilities, by estimating the parameters, and then while doing these things, with the distributions, so we maximize those distributions, estimates, probabilities of estimates, likelihood estimates. Actually, maximize the likelihood of estimates of the parameters. And with those parameters, you get the distributions, you compute the probabilities, and find out that where is the point of transitions from one class to other class. So that would give you a new threshold value, and you go on doing these things till you get a convergence. So there is also another method that that does not consider this kind of Bayesian approach, but it also consider some objective function, and that is also based on this probabilistic estimates, parameter estimations. Here, this is the objective functions that has been shown here. It is basically the between class variance, and this is how it is defining. You can see that this class variance is defined by the distance between two means of the likelihood estimations. So, and these are the class priors. So what in this case, what we do, that for every possible pixel, every possible value in the brightness range, we compute this in this quantity. So it's a kind of just a scanning from pixel value from 0 to 255. At each point, we compute this entity. Wherever it is maximum, we choose it as a threshold value. So we use the similar technique. Use once again, given a particular threshold value, we can compute all these quantities, and we get this computation. So the result of these two typical algorithms, one is Bayesian algorithm, another one is Odds-True thresholding algorithm. I will show you the result. So first is that Odds-True technique. Now with this particular document and the example what I have shown, it is found to be 157, and there now this is the result that you can see. So earlier also intuitively we took 157, somehow computation also we got it, and this is optimal in the sense that it takes care of not including noisy pixels and retaining most of the foreground pixels. Whereas in the Bayesian case also, very surprising, it also came 157. But no, when you look at this image, I have displayed it, actually you can see that they are not the same. It is more, this image looks more contrast, it has more contrast. Because what we did, we have processed the original image before applying the Bayesian classification. Because one of the problem of Bayesian classification, as we have considered in the previous example, we have seen that this histogram, we considered their modes are distinct. But if we look at this histogram, this mode is not very distinct, though it has a kind of mode information that we speak. But at this side, this mode is not very distinct. So what we did, that's why we have enhanced the image or stretched the image. That means the dynamic range of the image is increased. So it gives more contrast, and if I do that operations, we can see that the transformed image has a histogram spanning covering most the wider region of the range of the brightness value, and its peaks are also getting a bit prominent. So with this, your Bayesian classification algorithm works better, and incidentally it gets 157, but since we are applying it on the processed image, so you get a different result. So just to elaborate that part, that how we can do this kind of contrast enhancement. So the technique what we have applied there is simple pixel mapping technique. That means you have a input pixel value, and then in your processed image you just map that pixel value to another output pixel. Wherever that value is there, you just map it to an output pixel value. So you are defining a function, but this function should have a property. So as you understand from the visual point of view also, that the darker pixel should look darker even in the processed image, which means that if I have, so which means it should have a monotonically increasing function. That means if the value x1 is greater than x2, then the mapped function y1 should be also greater than y2. So you consider a pixel value x1 and pixel value x2. So this, according to this mapping function, say this is y1, and for x2 this is y2. So you can see that if x1 is, as x1 is greater than x2, similarly y1 is also greater than y2, right? So it ensures that monotonicity, and that is how it is basically through this the contrast reason. So one such function which I have shown here, what it does, it takes a cumulative distribution. It considers the cumulative distributions of the probability value, and you are multiplying with 255 because you are exploiting the full range. So this cumulative distribution, it can be shown that it tries to make histogram spread it, keeping its structure better. So it states the histogram with these distributions. So this is one example. Instead of textual image, I have shown you one satellite image of a satellite band, and this is the original image, which looks very less contrast image. But and you can see also that apparently it is clear from the histogram the effective dynamic range is just this is the effective dynamic range where all the pixels are concentrated. But once we apply the histogram equalization operation, the function which I have discussed, just described, that is cumulative probability distributions, that functions, take the cumulative probability distribution and use that as a function. So then once you apply the mapping and compute the histogram, then you can see this is how the histogram looks, and where these modes are also getting better distinct in this case, right? So this is one example of histogram equalization. So the next operation which we would like to discuss here is the segmentation of images. So we have discussed binarization, and in binarization we considered it is basically classification into two classes, whereas or I can say that partitioning of image pixels into two different, two distinct classes. But it could be very general. It is not only two; it could be multiple classes. So a segmentation considers a general case, not only binarization, but it could be multi-level classifications. And as I said, so the expectation maximization technique what we have used for the two-level classes, that could be extended to the bi-level classes. So that example, I will be just continuing that discussion. So we consider probabilistic modeling with mixture of densities. And in the previous case, I have taken only two densities, right? Two classes, only two probability densities. So let us understand what is meant by this. You can see this from this example, that when I have shown the previous example, I have taken only two classes. This is that likelihood part. So this one is giving you the probability, of x, and this is the contributions for each class, which is denoted by gi, and there are key classes. And for each one, we have this likelihood function, probability of x given gi and probability of gi. You know that actually this is nothing but the joint probability of x and gi. Right? So the mixture density. So this is how the mixture density. So each density, for each class, we have a probability distributions, and their proportion, they are mixing with these weighted values, probability of gi. So sum of probability of gi should be equal to k, should be equal to 1. So these are the number of components, and this is the component density. So instead of one threshold, I will be now considering multiple thresholds. Rather, instead of thresholds, in this case, what I will do, we will start with estimation of parameters of each components. Say, for example, these are parameters. So for describing this likelihood, if I consider each one is a normal distributions, for each one I will have two parameters which will characterize my normal distribution. One is mean and say standard deviation, mu I and sigma I for the I. And probability of gi is that class prior. So for each component, you have three parameters you have to estimate. So if you have k components, you have 3k parameters. So the whole histogram or whole probability density function is whatever is observed, that needs to be accounted by estimation of three parameters. So suppose if k is given to you, so what is the best mixing that would explain this probability density function. So that is why that is what this this modeling or this technique, and there we apply once again this expectation maximization technique. As I mentioned that we can use the Gaussian distribution, and I have discussed with respect to the histogram only single variable, that means brightness level, but you can consider an image for at every point you have certain feature vector denoting the characteristics of that pixels, and you are considering grouping all those pixel points with those feature vector itself. So it is just not histogram, on the image itself also you can do. So there, of course, in multi-dimension, these parameters get multi-dimensional parameters you have to consider. For Gaussian distribution, you have the mean vector mu I, and then you have the covariance matrix. So number of parameters will be large. So my explanations was with respect to the histogram, what I mentioned. So anyway, the algorithm is quite similar. This is the problem that we have to estimate all these parameters, this mean covariance matrix, mean vector, and also the class priors. So the algorithm would be, as I mentioned, that by doing parametric estimations of this covariance matrix and using the same expectation maximization algorithm by which you can do these estimations. So once again, you can start with an initial set, and then with that, once you specify everything, then you can compute each factor. That means you can compute for x what is the probability of its belonging to the kth Gaussian cluster. That means xi element, xi feature vector or xi pixel, whatever, belong to the kth Gaussian cluster. That is what is your, say, zik, and yeah, and of course, you have to use the corresponding normalization factor, because there is a discretization of the computations. That's why we perform normalization factors. Then this is the probability of computing, and then you can consider assignment of class assignment there, like the earlier case, but this part is little optional. You don't take this decision. What you do, that with this soft class assignment, consider every probability value as a weight of that class assignment to this pixel. So keep accounting that weighted factor while estimating the parameters in the weighted fashion. That means once you compute the parameters of a particular class, so you take into account of every pixels with those weights and compute those parameters, including its class prior, the mean vector and the covariance matrix, and go on doing these things. And finally, when it converges, then you can do hard assignments to make the segmentation. So one of the examples of multivariate thresholding, I applied it for histogram. So this analysis I did not apply to pixel level, histograms, and then computed those thresholds. And that's how now you get this multivariate threshold. So this is the example. So once again, I have used the enhanced image where the peaks are very prominent. So these are the thresholds which are obtained through this parametric estimation. So we have considered k equal to 3, and so these are the two thresholds we have obtained in between. So and then this is the segmented result by showing it different colors. So different intervals are displayed with different colors, as you can see. The intervals are shown here. So and so this is for the blue range. You can see the water is mostly reflected by blue, then green. So this is the greenish part, and yellowish part is more brighter range by the urban area. So all these segments are there. So with this, let me stop here today, and we will continue this discussion in the next lecture. Thank you for your listening.